starting with the Faraday's law, as we know that this law will give us the magnitude of induced EMF. And also, as we have performed the experiment and we have finally seen one conclusion that an EMF is induced on the coil or in a coil. And with this, the magnetic flux through coil was changing with time. So by studying these two phenomena, Faraday has performed one analysis and he shows a common fact that the time rate of change of magnetic flux through a coil induces EMF in it. That is the statement what we have written. And Faraday stated experimental observations in which the form of a law called Faraday's law and this law was for electromagnetic induction. And its statement which I am going to write at present. So its statement is like this: the magnitude of induced EMF in a coil, or you can say this coil is nothing but a closed circuit, is equal to the negative of the time rate of change of magnetic flux linked within it. So this is the statement, and now I am going to analyze this statement mathematically. So here I am assuming that the magnetic flux linked with a coil is equals to phi. Here I am time considered or the time interval is T. The change in flux is delta phi, and this change is taken place in the time interval delta t. So, with these two conditions, the Faraday's law I can state it as the average induced EMF, which I am taking as bracket epsilon, is equals to negative of time rate of change of momentum. So this is delta phi upon delta t. So see, I have just put the statement in the mathematical type of form. So this is your mathematical expression for Faraday's law. Now, here the negative sign is due to the direction of induced EMF, and this is with the help of or it seems the presence of the length law. So here you can easily assume that which pole is facing to the coil. So actually this is the north pole, and suppose I want to find out the induced EMF by a small time interval, so for which I consider a instantaneous property. Therefore, the instantaneous induced EMF is epsilon is equals to minus d phi by dt. So this is equation number 2, because this equation comes from what? So I am giving you a reason. This bracket will be cancelled because I am putting over here the limit sign for which the time interval tends to 0 and the remaining things are as it is. So by applying the limit, the delta symbol will convert it into d, which we have seen many times in the semester 1. Therefore, what this equation suggests actually, if the coil is made up of suppose n turns, so this is the simple case for only one turn in the coil, but suppose there are n turns, then there will be n number of magnetic field lines passing through the normal surface. So there is a change in the magnetic flux. So here 1 phi, instead of that we have to write n phi, and hence this equation number 2 will be modified in terms of epsilon is equals to minus d by dt. Instead of phi, now I am putting n phi. Now see, here n is the number of turns of a coil, but the number of turns will not change with respect to time. So this is the constant quantity, and hence any constant quantity I can put outside the integration or differentiation, and hence here the differentiation is there, so I can write minus n d phi by dt. And so this is my third equation, and with this the Faraday's law is over now. We will see now motional EMF. So what is the motional EMF and what is the steady EMF? That we will see in our next class.